Episode 5. This is the only episode in a series named after one axis of a framework we introduced in Episode 1, and it is the first time we reused that framework rather than just referring to it. 3 earlier episodes have pointed here. Episode 2 said that skipping the update operation gives you staleness, and that staleness is Episode 5. Episode 3 said that the append-only stream would be taken up here once it aged. Episode 4 ended on non-stationarity across sessions. All 3 were describing the same failure from different angles, and this episode is about naming it precisely enough to measure it. So this is a maintenance episode, and I make no apology for that. Most of what breaks in production breaks this way. Here is the failure, in the running agent. On the left, the claims triage agent reads an escalation threshold from the policy store and applies it. The answer is correct and the test suite passes. On the right, 11 months later, the same query against the same store, and the same confident answer. But the threshold was superseded. Nothing in the model changed. And here is the part that makes this hard, nothing in the store changed either. There is no error to catch. There is only an answer that stopped being true while nobody was looking at it. I have watched a version of this happen, and the hardest part was that nobody could say when it had started going wrong. The reason no test catches it is that a test is written at a moment. Correct asks whether it was right when written, and it was. Consistent asks whether it agrees with the rest of the store, and it does. Complete asks whether anything load-bearing is missing, and nothing is. Only one of the 4 axes asks the question that would have caught this: would this still be true if I checked today? That is the current axis, and it is the one axis of the 4 that degrades without anybody doing anything wrong. Everything from here is about turning that question into something you can run. Note also that it is the only axis of the 4 that degrades while you sleep. 3 objectives. Distinguish 4 different clocks and store all 4, because the whole episode follows from that one decision. Design an invalidation cascade cheap enough to run on every write. The constraint there is the interesting part, not the cascade. And define a staleness budget together with an audit that measures whether you are meeting it, because a budget nobody measures is a wish. I want to flag one thing about the middle third of this episode before we get to it. It is engineering practice rather than published results, and I will say so on the slides. I would rather label the boundary between literature and practice than let you discover it afterwards from the reference list. So start with the field almost every store has, one timestamp. What does it tell you? That something happened at some time. Now here are the 4 questions a long-lived store actually has to answer. When did the event itself occur? When did we come to know about it? Over what period does it hold? And when did anyone last check? 1 field, 4 questions, and only the first of them is answered. In a store that outlives a single release cycle, those 4 answers diverge from one another, which means the single timestamp is not merely lossy. Applied to the wrong question, it is wrong. Most stores have exactly 1, and most of them were designed by someone who knew that and shipped anyway. So store 4. Event time, when it happened in the world. Ingest time, when it entered the store, and those 2 are different every time you import a file or backfill a log. Validity interval, from when, and until when, it holds. And last verified, when anybody last confirmed it against a source. I want to be exact about attribution here. This 4-clock scheme is ours. It is a direct application of standard bitemporal database practice to agent memory, and it is not a claim from any paper in this series. The 4th clock is the one that is almost never present, and it is the one the audit later needs. 2 axes make this concrete. Event time runs horizontally, ingest time vertically. One fact is a bar, it holds over some span of event time, and it is known to us from some point in ingest time onwards. Now watch a correction arrive, the same event, re-ingested later with a different value. The earlier bar does not vanish. It closes. And that distinction is the entire mechanical difference between a store you can ask historical questions of and a store you have been overwriting. Deleting the old value destroys the only evidence that you ever believed something else, which is exactly the evidence an audit needs. The vertical axis is the one people leave out, and leaving it out is what makes corrections destructive. Each clock buys you one question. Event time, what was true then? Ingest time, what did we know then, and therefore, was the decision the agent made at that moment a reasonable one given what it had? Validity interval, is it true now? Last verified, how much should I trust that answer? The second row is the one that matters when somebody asks you to account for a decision, because without ingest time you cannot distinguish a bad decision from a decision made on the information available. And the fourth is the one the freshness audit needs. Neither is recoverable from a single timestamp after the fact. For clocks buy 4 questions, and the mapping is 1-to-1, which is a good sign that the scheme is not overbuilt. Which raises a question worth 2 minutes. We spent a whole episode on 3 competing taxonomies of agent memory. What do they say about time? Our 06 dynamics axis is formed, evolved, retrieved. It describes how a memory changes and says nothing about when it expires. Our 07's management loop has an updating stage, but updating there is triggered by new input arriving, not by something becoming untrue. There is no notion of validity in it at all. So time is missing from this field's own vocabulary. Not underweight, absent. The 4 clocks are not a refinement of either taxonomy, they are a dimension neither of them has. Which is a reasonable thing to notice about a field this young. The structural fix is to stop overwriting. A fact becomes a chain of versions. The threshold was 50,000, then 75, then 90, each with the interval over which it held. And the index is built over those validity intervals rather than over insertion order, which is what lets a query name a time and get back the version that held then. There is a cost and it should be stated, the store now grows with every correction instead of staying flat. That is the price of being able to ask historical questions at all, and in my experience it is a price people are happy to pay once they have been asked a historical question they could not answer. And once the store is versioned, one more capability becomes available, and it has a name. A retrieval can ask for the store as it stood at a chosen time, rather than as it stands now. That is the requested state view, and both the term and the mechanism are our 35s. The underlying idea is the as-of query from temporal databases, and our 35 is the work that brings it into agent memory. What it buys is that one store can answer 2 different questions: what do we believe, and what did we believe? When somebody is asking you to account for a decision the agent made last March, the second question is the one they are actually asking. That work's title makes a claim I want to draw out, because it is a methodological point rather than a mechanism. Failures that involve state look like one bug and are not. The agent cannot order events in time, that is temporal reasoning. 2 versions both match the query and the wrong one wins, that is version conflict. And the answer is served confidently past its validity, that is not knowing you are stale. The evidence that these are separate is in the reporting itself, 2 distinct metrics on 2 distinct benchmarks. A single number could not have separated them. Note which of the 3 has no metric at all. We come back to it. When 2 versions both match a query, you need a resolution rule, and there are 3 cases rather than 1. If the intervals are disjoint, the query time picks 1 and there is nothing to resolve. If they overlap, both held at the query time, and recency is not a rule, you need a written precedence policy, because whichever version happens to be indexed first is otherwise the answer. And if one interval is open-ended, ask whether it is genuinely still open or whether nobody ever closed it. Those are different situations and the 4th clock is what distinguishes them. Recency alone resolves only the first case, which is why stores go wrong quietly rather than loudly. Here are the numbers. Temporal F1 on LocoMO goes from 0.0295 to 0.1705. Conflict accuracy on LTP improves by 0.240 absolute. Read the first one carefully, because the baseline is the interesting part. A temporal F1 of 0.0295 is not a weak baseline, it is essentially 0. The capability was absent rather than poor. A near-zero baseline tells you something a mid-range baseline cannot, that the problem had not been addressed, rather than addressed badly. And the two numbers sit on different benchmarks by design, which is the decoupling argument from the last slide carried into the evaluation. Now the part of this episode that is engineering rather than literature, and I will mark it as such on every slide. Memory is not flat, a summary depends on the events it summarized, a reflection depends on the records it was drawn from, a learned rule depends on the cases that taught it. So when you supersede one input, every derived item above it is now suspect. Suspect, not wrong, those are different states, and only one of them is actionable. The consequence for implementation is immediate and often missed. The dependency edges have to be recorded at derivation time, because you cannot reconstruct them afterwards from the artifacts. So here is the cascade. One fact at the bottom of the graph is superseded. The ripple travels up through everything derived from it, and, crucially, only through that. Each item it touches is marked suspect rather than deleted, because deletion is a decision and the cascade is not entitled to make it. A human or a stated policy decides what happens next. Now watch where the ripple stops. Most of the graph is never touched, because most of it has no path to the superseded record. If your ripple does not stop, you do not have a cascade. You have a rebuild with extra steps. And marking rather than deleting is what keeps the cascade cheap enough to be allowed to run at all. Which gives the real design constraint, and it is not the one people reach for. A cascade that can touch the whole store cannot run on every write, so it gets demoted to a nightly job. And the window between a supersession and its consequences being propagated is then measured in hours, and that window is exactly when wrong answers get served with full confidence. A bounded cascade, whose worst case you can state in advance as a function of graph shape, runs inline at write time and closes the window. So the target is not a fast cascade. It is a cascade whose worst case you can state before you deploy and measure afterwards. And when the cascade has marked something suspect, there are two things you can do, which people tend to conflate. You can recompute, regenerate every suspect summary from its inputs. That is correct and expensive, and it has a subtler cost. It changes text nobody asked to have changed, so the resulting diff is unreviewable. Or you can recheck, test whether each suspect item's claim still follows from its current inputs. That is cheaper, and it produces a short list a human can actually read. This is the same shape as episode 4, slide 21, local maintenance beats global reorganization. 2 episodes, 2 mechanisms, 1 lesson. An unreviewable diff is not a safe change, however correct the computation behind it was. One more thing before we make this measurable. Who decides when to recheck? Episode 4's third axis learns a read-side policy, when to retrieve, what, how much, when to merge or forget. When to recheck is the same kind of decision, taken at the same point in the loop, on the same interface. Which means freshness does not need a new subsystem. It needs one more action in an action space that somebody is already learning over. And notice where it lands, in the one row of episode 4's grid that had a claimant on every axis, which was forget. Rechecking is what you do instead of forgetting when you are not sure yet. Now make it measurable, and the first move is to stop treating the store as one thing. A policy rule ages because the rule is amended, and its budget is days. A case precedent ages because later cases supersede it, and its budget is months. A user preference ages because the person changed their mind, and it has to be revocable on request regardless of budget. A procedure is tied to the release cycle of whatever it describes. And a derived summary has no fixed budget at all, it inherits the tightest budget among its inputs, which is a rule rather than a duration. One number for the whole store is always wrong. Then the audit, and the important word in it is scheduled. This is a job, not an exception handler. It reports the distribution of ages against the budget for each class rather than a pass or a fail, because a distribution tells you where you are heading and a Boolean does not. It runs whether or not anything looks wrong, and that is the whole point, because staleness produces no symptom at all until it produces a wrong answer. And its output should be a number you can put in a review: what fraction of served retrievals were inside budget this month. If the audit only runs after an incident, it is not an audit. It is a post-mortem with better tooling. And here is what that looks like over time. Simulated time advances, and each retrieval adds the age of the item it served to a histogram. The budget line sits at a fixed age and does not move, the distribution drifts rightwards underneath it. The audit fires when the fraction of mass beyond the line crosses a threshold, not when a single item crosses it, because one stale item is a fact of life and a shifting distribution is a system problem. And note the label in the corner: this is a simulation, illustrative of the shape. It is not measured data, and I would rather say so on the slide than have you take a number off it. All of which has a storage consequence, and it is easier to state as what each field makes possible than as a schema. Source, where it came from, specifically enough that you can go back and recheck. Without it you can only rederive, not verify. The 4 clocks, and without last verified you cannot run the audit at all. Derivation, which items this one was computed from, without it you cannot cascade, which makes the previous 5 slides unimplementable. And the writer, which policy, rule or model version produced it, without that you cannot attribute a bad write to anything, which means you cannot fix the cause, only the symptom. Which finally gives a decision procedure, and it has 3 outcomes rather than 2. A retrieval returns an item. If it is inside budget, answer, and record that it was served inside budget, because that record is what the audit counts. If it is outside budget but verifiable right now, flag it, recheck it against the source, then answer with the result and a new last verified time. And if it is outside budget and not verifiable, abstain, which means saying what you would need in order to answer, not simply declining. Abstention is one of the 5 capabilities that are 55 scores, so this is not an exotic requirement. It is the branch most systems do not have. So how well is any of this measured? One suite scores 5 capabilities, one of which is abstention, and reports roughly a 30% accuracy drop under its conditions across 500 questions. 2 things in there are worth separating. Its framework has 3 stages: indexing, retrieval and reading, and that matters for diagnosis, because a failure at reading is not a failure at retrieval and a single accuracy number hides which one you have. And abstention being scored at all is the notable part. Most suites reward answering and are silent on declining. As for the 30%, it is conditional on that suite setting. Quote it with the condition or do not quote it. The other suite is the scale point, 451 questions over up to 500 trajectories and 115 million tokens, and it is text rather than multimodal. Scale is not a vanity number for this episode's question, and here is why. A short benchmark cannot contain a fact that expired, because nothing in it has had time to expire. So staleness only becomes observable at horizons like this one. I want to be clear that this is our reading of why the scale matters rather than a claim the suite itself makes. And one correction worth stating plainly: the 115 million tokens is real, the multimodal part is not. Which leaves one thing unresolved, and I want to end on it rather than paper over it. Both suites score whether the right item was retrieved and whether the answer built on it was right. Neither scores whether the agent knew its answer had expired. Abstention is scored as a capability: can you decline? But being right about your own staleness is not the same thing as being willing to decline. That is the measurement gap this episode leaves open. And it is exactly slide 12's third card, the one that had no metric next to it. Episode 12 picks it up, as a benchmark design problem rather than an engineering one. Lab 5. Add the 4 clocks to your store, backfill event and ingest time from the log, and set validity and last verified by hand for one class of item, because one class is enough to learn from. Replay the log, and for every retrieval record the age of what was served and whether it was inside budget. Then count how many retrieved items were already expired at the moment they were served. 30 lines or so against the claims triage corpus in the repository. That count in step 3 is the most alarming number in these 5 labs, and it costs about an afternoon to obtain. Bring the number to episode 12, where we ask what a benchmark would have to do to catch it. 5 takeaways. 1 timestamp guarantees a future error, so store 4 clocks, event, ingest, validity, last verified. Time is absent from this field's taxonomies, and that is worth remembering the next time one is offered to you as complete. A cascade whose worst case you cannot state cannot run on every write, which means it will not run in time. Recheck rather than recompute, and give every memory class its own budget rather than the store one number. And 3 outcomes rather than 2, answer, flag, or abstain. Next episode we leave the control segment and start on self-evolution, what changes, when, how, and where. That segment boundary is a real change of subject. Everything so far has been about managing memory, and what follows is about changing the agent.